Welcome to lecture 21. Let's consider the idea of adjoints and constructing functionals out of governing equations. So let's first consider the problem of a beam, and it's pinned here, and you have a torsional spring there with spring constant alpha. And then here we have a stiffness K spring with a distributed load Q of X. And we want to determine the governing equation for this system, using the the order Bernoulli beam theory. And so we're going to start using that formulation. Step one, we want to examine what are displacement assumptions for this theory. And in this theory, we're going to assume that there's no axial deflection, so it's all due to bending. Okay, and then the outer plane deflection is 0. The transverse deflection is W, and all the axial deflection is only due to bending, the slope. So step two, the only non-zero strain is epsilon xx, which is minus z w double prime x, because that is basically this. And so when I plug that here, I get this expression. And then now I have to form the total potential energy, which is really pi equals, and here the only variable of interest is w of x. So that's a triple integral of 1/2 sigma xx epsilon xx, because the other strains are 0, so there's no, the rest of the terms do not show up. I also have then the potential energy due to loads applied. Only in the top surface, only in this surface here, the top surface, and I'll call it Q. And I have some spring constants whose energy can be found, and you can check it in physics, can be found to be K. And then you have the deflection at the end. And then you have the spring constant alpha, and then W prime 0 squared, because a torsional spring constant is usually uh, going to be related through the slope at this point. So I think that makes sense. Here, what you're going to find is that W does not depend on ds, does not depend on dy. So if outer plane is dy and the x-axis is dx, wx does not depend on dy. So you can bring it here, and what you will get here is basically integral 0 to L q bar w of x dx, especially if this length is L and I start x from here. So that's what we get. And then this one here is easy. Uh, Triple integral 1/2 e epsilon xx squared dx, and I have z squared w double prime squared d. Again, I'm forgetting here the volume here, and here is dA dx. This does not depend on dA. E does not depend on dA. So the double integral of z squared dA is I. So I get integral 0 to L ei w double prime squared dx, 1/2 here. So the total potential energy for this beam, which is an Euler-Bernoulli beam theory, is found to be pi equals 0 to L 1/2 ei w double prime squared minus qw, and I call it bar. I don't have to write as a function of x because we know it's a function of x. Dx plus 1/2 k w at L squared plus 1/2 alpha w prime at 0 squared. And what I want to do now is invoke the theorem of total potential energy. And the theorem of total potential energy states that for every kinematical deflection W, that deflection W that renders pi stationary, or the total potential energy stationary, is the one that renders the system in equilibrium. So, in other words, I need to find the first variation of pi equals 0. And when I do that, and I find the W that renders the pi stationary, then I get 0 to L ei w double prime del w double prime minus q bar del w dx plus k wl del wl plus alpha w prime 0 del w prime 0. So that's what I get for the first variation of pi, and I set all that equal to 0. And so now I have to integrate this term by parts to get rid of this double derivative, which I'll do now. Ei double double prime del w double prime ei w double prime prime del w prime ei w double prime del w plus minus plus. And then I get now that the first variation of pi is equal to 0 to L. I can factor del w now. ei double prime minus q bar dx. And now I have a bunch of boundary terms. Plus ei double prime del w prime. And that's at x equals 0. Minus ei double prime del w prime at, and again, this will be at x equals L, x equals 0. And then now I have another one, which is minus ei w double prime, prime on that, del w at x equals L, plus EI W prime prime del W x equals 0. And then I have these terms that need to be added. So let me call this A, and I'll just add it here, plus A equals 0. Now I have the group terms, but before I do that, I can invoke the fundamental lemma of calculus variations. Step 6, invoke the fundamental lemma of calculus of variations. And if I do that for any del W, the Euler-Lagrange equation is EI W prime double prime minus Q equals 0 between 0 and L. And the boundary conditions at x equals 0 are as follows. So in this case, the boundary condition at x equals 0 can be looked at by notice how this term and this term can come together. And so I have minus EI W double prime, so that's this term right here, and I'll add it to the one at the top, plus alpha W0 is 0, or, and I don't have to write W00, or, and that's that term here, I apologize, it's W prime, or we have W prime specified. And you cannot do both, it's either one or the other. Clearly W prime is not specified, so the boundary condition is this one here, because I'm not specifying the slope. I'm not specifying the slope at that boundary. At this boundary, we're not specifying the slope. And then at x equals 0, I have another condition, which is here at the bottom right. And you can see here that either EI double prime prime is 0, or W is specified at the same boundary x equals 0. And I group terms there, and I want you to notice I did that. In this case, we could state that W is specified and it is equal to 0, because you can see there that in our situation we have a pin condition here, so it cannot move up and down. Boundary conditions at x equals L can now be found, and we can find that by looking at this term here, which combines with that term. And that's going to be minus EI double prime prime, which is combining with plus K W equals 0, or W is specified. At the right boundary, we're not specifying W, so this has to be 0, and that should be the boundary condition at x equals L. Again, these are the natural ones, and those are the essential ones. The essential ones on the right. And then we have finally this boundary condition here. Either that is 0, or W prime is specified. In our case, we're not specifying W prime, so this has to be equal to 0. And so those are the boundary conditions that we find. Um, and we find the governing equation and the boundary conditions. And note, very important point to note, I should square this so it's clear. Very important point to note is that if you solve for W out of this set of conditions, that W is the one that minimizes pi and is the one that renders the system in equilibrium. Meaning, when you apply these loads here with these types of springs and torsion springs, is the beam is going to deform. That deformation you will find by solving these equations. And when you solve these equations, that W that comes out of here is the one that minimizes pi and is also the one that renders the system in equilibrium. So what I want to cover now is the idea of an adjoint problem. And you know what I want to do is try to show you before I get there, if I were to be given this order Lagrange equation, these boundary conditions here, can I construct a functional? And if a function, if the governing equations represent a conservative system, then a functional will exist. And so we can form the functional for any problem. And the way we do that is that we take then a functional will exist and you can determine the functional. And the first step in determining the functional start with the governing equation, this governing equation here. So let's start with that and see if we can get to the governing equation. So the first step in the process is to multiply the governing equation by a test function. And that test function has to satisfy the boundary conditions of the problem. So I'm going to start with this, multiply both sides by a test function, which satisfies the boundary conditions of the problem, meaning if I have any essential boundary conditions, I want to make sure that V is 0 at that boundary because I'm going to treat this like del W basically. In fact, I'll multiply by del W so it's clear that anything specified on W needs to be considered. Del W, and consider this to be the test function. And my goal is to start from here and construct a functional. That's the goal of this exercise here. It is convenient because if you can construct a functional from there, you can potentially use approximation methods that allow you to solve the problem. So I'm gonna now go ahead and integrate by parts. And what I want to do is to take this double prime and see if I can put it here on this side. So I split derivatives the best I can. And so to do that, I'll start with the del W on the left. And now I'll switch derivatives to the left. And when I do that, I'm going to get the following. And I'm just computing, just putting all the boundary conditions here. And this is equal to 0. So what I want to do next is I want to use the boundary conditions that I have. And I'm going to use the boundary conditions and substitute them in. For example, EI W prime prime, for example, here at x equals L, I know what this is. So what is that? We know that at that boundary at x equals L is equal to KW. So I'll plug it in here, KW. You can see that there. At this boundary, x equals 0, W specified. So this doesn't show up. At x equals L, for example, this is 0. There's no moment. You can see that from this boundary here. And then this one here at x equals 0, we know what this is. It's provided to us as alpha W prime. And you can see that from this equation here. You can solve for EI W prime and plug it in here so you get that. So then what I end up getting is the following. We get the following, which I'll call the weak form. And so if I do that, I get the integral from 0 to L, EI W prime, del W prime, minus Q del W dx. And then I have plus alpha W prime del W prime plus K. And this is at 0 plus K W prime at L, and not prime, but just like that. And this is, I apologize. So I get this. So to form the functional is very simple. Anytime you see the W repeated like that, you're going to turn that into 1/2. And so that's how you construct the functional. So now the functional can be constructed as follow: 0L 1/2 EI W prime. And we're going to make this del W prime into W prime. So you get W prime minus Q W. Anytime you see del W, you're going to convert into W alone. plus, and then again here, 1/2 because it shows up both here and here. So 1/2 alpha W prime at 0 times W prime at 0 plus 1/2 K W at L W at L. And you can see here quickly that's the square. And so that's my functional pi. So I started with a governing equation here, and my goal was to use the boundary conditions to come up with the functional for the problem. And so, yeah, a functional exists in this case because it's a conservative deformation process. You can see I derived this starting from the total potential energy, but I was able to arrive to the total potential energy by starting from the boundary conditions. You can do that in the cases where the system is an adjoint, self-adjoint. So let me cover the idea of self-adjointness. So define, and if the system is self-adjoint, then it is a conservative system and a functional will exist. If it is a functional, most likely it's a quadratic functional. And it is a minimum at stationarity. So we define an inner product as follows: W, comma Z equals 0 to L W times Z dx. And if W and Z are orthogonal functions, then W comma Z is 0. So we define a self-adjoint system as follows. Consider an operator equation of the form AW minus F equals 0, where A is a differential operator. That operates on W. And F, in this case, F is independent of W. So in our scenario, for the case of EI W4 primes minus Q bar equals 0, the differential operator is A equals the partial or not partial because differential, like that. And so how do we determine whether a system is self-adjoint? So let Z be an unknown function in the adjoint system. So then I'm going to have the following: 0 to L, Z, I'm going to multiply this by Z, EI W4 primes dx, and I want to check if I can recover, if I switch W and Z, if I can get W, EI W4 primes, sorry, with Z here. If I can make this happen, then I definitely have an adjoint system. Somehow I have to make sure that this is equal to that somehow, that this system, when I shift W and C and switch it, I'll get the other system. And so that's what I'm trying to do. I'm trying to figure out whether a system is self-adjoint, if it is, a functional does exist. And the benefit of determining that is that if you can determine whether a functional exists, then you can go through this procedure, get the functional, and then you'll see later that this can be very powerful. So yeah, so we want to make sure, we want to see if it's a self-adjoint exists. And so my first step is to integrate by parts, but I want to integrate by parts completely. I want to bring all these fours to this side, because that way I get a step closer to getting it on like what's on the right hand side. So that's my goal. So let me start from the left hand side, and my goal is to arrive to the right hand side. So to do that, put Z on the left side like this, and I could have done this double prime like that to be more exact, because that's how the Governing equation looked like. Z prime, and then I'll keep removing derivatives. And yeah, I'll continue doing it until all of them are removed. And then I'll do a plus, minus, plus, minus, and plus. And I'm integrating parts. The bottom term goes inside the integral. And you can already see that this matches that. But I'm stuck now with some boundary conditions. Plus EI W prime prime times Z. And this at x equals L. And then next I'm going to have minus EI W prime Z prime at x equals L. And then I have plus the minus here so I don't lose it. And then yet I continue to have terms minus EI like that. So we should check that everything is in order. That looks right. That looks wrong. That should be a Z here. And then I have this term, which matches what I have. That looks good. This is good. This is good. This is good. And this is good. And so somehow for the left-hand side to be equal to the right-hand side, all these boundary conditions have to vanish, the ones on the right. They all have to go away somehow. And so I really have to look at that carefully. You can see that at x equals 0, ei w double prime. So you can see that this term right here is alpha w prime. This one right here is alpha w prime. So I can substitute that one there as an example. You can see here that at x equals 0, I have a pin condition and w0. So this term goes away because w0 at x equals 0. If you recall, it was a beam. It was pin here, spring here, and a spring constant here. So at x equals 0, definitely w equals 0 is pinned. You can see that there. So I've substituted that as it goes to 0. This is taken care of, and the remaining terms um, are as you see. So you can now see you can now see well let's look at x equals L now. So at x equals L, I can now also substitute the boundary conditions. If I look at that term, if you recall, ei w double prime is 0 from the boundary conditions. So substitute the boundary conditions, that goes to 0. And if you recall at x equals L, ei w prime triple prime, ei w triple prime, where is that term? That's right here at x equals L. So this term right here was found to be, from the boundary conditions, we know that that's kw. So we know that from the boundary conditions. So now what I can do is examine the boundary conditions. So I'll continue to the next page. So please keep track of what we're doing. At x equals 0, anything that has x equals 0, I'm going to write in the next page. And I want that to be equal to 0. So what I want to do then is factor out w prime out of here. And you can see that for this to be equal to 0, I need at x equals 0. I need that at x equals to 0. And I want to factor out yeah, so for this to be equal to 0, I need z to be 0. And I also need this to be 0. At x equals L, I'll write all the terms again, one by one. And I'll factor W here to get factor W prime there. And for me to make that equal to 0, this needs to be equal to 0. So KZ and now finally I have EI Z double prime is 0. So those are the boundary conditions x equals to L. If I can set this equal to 0, then I can make the left hand side equal to the right hand side. So I'm able to switch everything from Z to W successfully, and I'm able to make the boundary conditions vanish. So I need to compare now the boundary conditions. System 1 that I started with, and system 2, which in Z. So this is in W, and this is the adjoint. This is the adjoint. Notice I'm able to make this happen. I'm able to switch Z and W and get that through. If I'm able to do that, that's great. I was able to do that here. You can see that here. My next goal is that the boundary conditions vanish. I came up with the boundary conditions in Z so that all that stuff vanishes. Now I have to compare these boundary conditions to the original system to see if I can switch Z and W. So at x equals 0, earlier I had shown that I have W equals 0. And I also had alpha W prime minus EI W double prime equals 0. At x equals L, I also had EI W double prime is 0 and KW minus EI W triple prime equals 0. I apologize for that. If I look at the adjoint system, all I'm going to do then is transcribe all these to the next page, and I get Z equals 0, alpha Z prime minus EI Z double prime is 0, and EI Z double prime is 0, and KZ minus EI Z triple prime is 0. You can see here very quickly that I can swap W and Z, and I get the same system visually. So therefore, this system is self-adjoint and a quadratic functional exists. And you can see that I was able to get it earlier. I was able to get the quadratic functional. This is what I got. So obviously, it does exist and it's doable. And so this example shows you